I'll begin with a word of prayer. So, Heavenly Father, we thank you for this day. I thank you for the students. Just ask you to bless this class today, Lord. In your name I pray. Amen. So did you guys enjoy the bonus battle yesterday? Was it exciting?
Yes.
All right. Did Sam actually help you?
Yes.
Okay, good. You missed. Oh, I should have given them the hammer. Oh, man, I missed out. Did Sam wanted to use the hammer? Yeah, I didn't. I'm sorry. He's not worthy. What can I tell you? Make sure you tell him I said that. Let's see here. So let me work an example, which I think will be helpful. Suppose we're trying to solve dy dx equal to e to the y squared times the sine of x to the 7th. All right. So this is, obviously find the general solution. All right. Find the implicit general solution. So that's my task, to find the implicit general solution of this. All right. Well, you guys know maybe a little bit by now how to solve different. I think you know. I think you could have done this without me, maybe, if you just poked in the right direction. To separate variables, right? The idea that this is going to be dy over e to the y squared equals the sine of x to the 7th dx, right? I think everybody here can do that. Separate variables, right? And a subset of you will realize, oh, that's e to the minus y squared dy, right? Great. And then at this point, you'll be stuck, right? Because do you know how to integrate e to the minus y squared? Do you know how to integrate sine of x to the 7th? The answer to that may or may not be yes. It's certainly, probably, almost certainly categorically no if you don't know about power series. But we do know about power series. We know about Maclaurin series when we can change those integrands to corresponding power series, right? I can trade an e to the minus y squared for the sum n equals 0 to infinity of minus y squared to the n divided by n factorial, right? dy. And on the other side, the integral of the sum n equals 0 to infinity minus 1 to the n over 2n plus 1 factorial x to the 7th parentheses to the 2n plus 1, right? I made a substitution here on the left-hand side using the known Maclaurin series for the exponential function, and on the right-hand side using the known Maclaurin series for the sine function, which I told you should memorize, right? It's still true that you should memorize them, all right? And then, okay, well, we can simplify this, right? This is the sum. All right, so this is the sum n equals 0 to infinity of minus 1 to the n, y to the 2n divided by n factorial, right? Minus 1 to the n over 2n plus 1 factorial, x to the what? X to the 14n plus 7. So then using the term-by-term integration theorem, we find the answer, right? The answer here looks like this. So the sum n equals 0 to infinity minus 1 to the n over n factorial, 1 over 2n plus 1 y to the 2n plus 1 equal to the sum n equals 0 to infinity minus 1 to the n divided by 2n plus 1 factorial 1 over 14n plus 8 x to the 14n plus 8. All right, and then you guys, where do you want to add the constant? What's that? To the x side? Okay. I mean, you can't be wrong. Wherever you put it, it's good. And in this problem, at least. There you go. That's the answer. See, because the best we can do here is to find a power series form for the answer. If I want to alert you to the fact that that's what I'm looking for, I might make the instructions to the problem say, find a power series solution to this differential equation. This is a power series solution. Yeah. Integrated. So basically the theorem, the term-by-term integration theorem amounts to this. You can erase this here and put it here. That's really all I'm saying. It says you can pass the integral inside the series and go term by term. With the understanding you group all the constants together. Now I promised one of you another example before class. Let me get to that one. If you don't mind, I'm going to change it ever so slightly. Y prime prime plus 4y equals to 0, given y of 0 equal to 0, and y prime of 0 equals to 1. So I worked out a problem like this in class, and then I was asked, was it on the test? And I think I said some kind of wandering, maybe it is, maybe it isn't kind of. And then I kind of said it wasn't. I should qualify that. It could be on the test. It's in your homework. It's a reasonable question. It would be something I would consider more of a bonus question on the test, but it could in principle be on the test where, you know, you'd earn points from it. But you probably could make an A on the test without acing this problem just the same, all right? But the point here is that we can solve this problem using power series. Your homework problem is actually easier than what I did in class because the homework problem you're given, which problem am I talking about? Hannah, what was it? 119 or 109? So what I'm doing is like 109, all right? And it's different than what I did in class. The main distinction between what I did in class, you know, is that I'm given initial conditions in this problem. When I worked in class before, we were not given initial conditions. So I had like a C0 and a C1 in the final answer. But this one we're given initial conditions. So the general technique is just to suppose y is a power series. Well, I'll just write it out. So let's say the sum n equals 0 to infinity of Cn x to the n. All right? Notice y of 0 equals to C0, and y prime of 0 is equal to C1. How do I know that? This is Taylor's theorem, right? That the coefficients to the power series are related to the function evaluated at 0, then the derivative evaluated at 0, then the second derivative evaluated at 0 divided by 2, and so forth. So I'm given that the position and the velocity are 0 and 1 respective. That means that this says, in other words, for this problem, C0 is equal to 0, and C1 is equal to 1. If you'll allow me, so just, you know, in the plus dot 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 notation, we have y is equal to, you know, C0 plus C1x plus C2x squared plus C3x cubed plus dot dot dot, right? So what I'm saying is just that this one is y of 0, and that coefficient is y prime of 0, all right? But here we're told that those are 0 and 1. So that means that my power series solution looks like y equals to x plus c2x squared plus c3x cubed, and so forth, all right? So let's just calculate out to like the, I don't know, 4th order or something. Maybe let's calculate to the 5th or, I think 5th order will be enough. If we calculate to the 5th order, we probably should be able to see the pattern. See if we can see it. Well, I debate here whether or not we'll be able to see the pattern. We'll try, see if you guys can see it. I don't know. If this doesn't work, we'll have to try a different approach. So y prime is what? 1 plus 2c2x plus c3x squared plus 4c4x cubed plus 5c5x to the 4th, right? I hope, do you understand what I'm doing? I'm just differentiating the power series term by term. Then calculate the second derivative. 2c2 plus 6c3x 12c4x squared, 20c5x cubed. So if we want this power series to be a solution to the differential equation, that means that when we plug it into the differential equation, it has to work, right? So we then substitute this. I can't spell substitute today. Substitute into y prime prime plus 4y equal to 0. Your problem 109 is easier because that 4 is a 1. So part of the difficulty of my example today is not even present in your homework problem. Okay, so what's y prime prime? 2c2 plus 6c3 plus 12c4x squared plus 20c5 x cubed plus dot, 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 and then 4y prime. So plus 4 times what? What was y? X plus c2x squared, c3x cubed, c4x to the 4th. Well, I'll just go to cube. I've only got the cubes over here. I'll only go to cubes over here as well. All right, there we go. All right. Now what? We want to choose coefficients C0, C1, C2, C3, C4, etc. that make the solution work. Now, 2 of those choices are out of our hands already because the initial conditions forced upon us this time that C0 was 0 and C1 was 1. So we don't even have any choice in the matter there, all right? You're stuck with it. Let's see what else we learned from this, though. The constant terms, what do we get? We've got 2c2. Any other constants here? Nope. Any constants here? No. So 2c2 is equal to 0. Therefore, c2 is equal to 0. How about the x terms? 6c3, right? From this side. How about over here? Equal to? Looks like 4, yeah? So C3 is equal to, 4/6 or 2/3, but I'm going to write it as 4 over 3 factorial for my own selfish reasons. X squared. But you're right, it's 2/3. I don't disagree. I just have other irons in the fire here. 12C4, which you wouldn't know until you get to the end of the problem. Okay, so 12C4, I'll shut up. 12C4 is the coefficient of x squared. On the other term, what is it? Plus 4C2, yeah? Uh-oh. Looks like C4 is 0. See, because if C2 is 0, then that makes C4 is 0. If you look at this, we're starting to see the pattern. This differential equation links every other power of x. So like the even powers are all linked together, the coefficients of the even powers are all linked together, and the odd powers of the coefficients are all linked together by the differential equation. That's what's happening. How about x cubed? What do we got? 20c5 plus 4c3. So what's that tell us? That tells us c5 is equal to minus 4c3 over 20, which I will look at as, did I get that right? Oh, yeah. You're right, absolutely right. They should have. Oh, I set this equal to 4. Come on, guys. Don't let me get away with that. That's crazy. That's crazy. Come on. I mean, sorry, I will keep the politically incorrect joke I was about to tell myself. Let's see here. There we go. So that means minus. Yeah, thank you. Which means that this one gets minus a minus, right? Minus 4 over 20 times 3 factorial. What's that? What's 20 times 3 factorial? Let me write it out a different way. That's minus 4 squared. Oh, I heard a 5 factorial. Yeah, that was what I was fishing for. So that's 5 times 4 times 3 times 2 times 1, also known as minus 4 squared over 5 factorial. So if you're good with pattern matching and you didn't have the misfortune of simplifying it to 2/3 early on, then you would see from this that the general pattern here is c to the 2n plus 1 is equal to what? Minus 4 to the what? So here 2n plus 1 equals to 3 and n equals to 1. Here 2n plus 1 equals to 5, so my n is 2, just so you can see the pattern. See, I've got a minus 4 to the n. Was that right? Minus 4 to the n? Yeah, I think so. Minus 4 to the n divided by what? 2n plus 1 factorial? Oh, and so if you tilt your head and squint, you can see that this is minus 1 to the n over 2n plus 1 factorial times 2 to the 2n I'm sorry, guys. Let me just stop that. Let's go back to the answer. What do we got for our answer? Y equals to, what was it? Summarizing, we got x. What's next? Plus what? Yeah, plus 0, plus minus what? Yeah, 4 over 3 factorial is the way I was writing it. I don't know if that's good or not. X cubed. And then what's next? Plus 16 over 5 factorial x to the 5th plus dot, dot, dot. I'm sorry, I should have just worked your homework problem like I was going to do originally. Adding the 4 makes it like a lot harder. What happens if the 4 is not here? We go through the same calculation. Without the 4, what would the same series of steps lead us to? It would be the series for sine, right? The 4's would be gone, and we just have like x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5th plus dot, dot, dot. So like your homework problem should work out to sine, the series for sine when you do it. This should be, oh, I know what I have to do. It's a little bit sneaky, but to see what this is, you have to have the insight to divide by 2. And that gives you 2x minus 1 over 3 factorial 2x cubed plus 1 over 5 factorial 2x. So I should have made this your homework problem. It would have been, not as easy. But I didn't. Oh well, too late. So, but the thing is, I had to have the insight, and this is what I was struggling with a second ago, to factor out the half to see the pattern that I needed. See, because now this is what? That's sine of 2x, right? So 1/2 sine of 2x is the solution for my stated problem in here. You notice that y of 0 is 1/2 sine of 0, right? And y prime of 0 is what? So I needed that half to compensate the 2 from the chain rule and the sine 2x. Yep. Oh, that is using the things that I've already done. So the C3, this was C3, so that appears as the coefficient of x cubed, because that's what C3 means. It's the coefficient of x cubed. And C5 is this. What is C5? C5 is the coefficient, oh, I didn't write it down. C5 is the coefficient of x to the 5th. So once I know what C5 is, it tells me that, I put that here. That's the coefficient of x to the 5th in the answer. So that's it. Yep.
How did you determine from the power series 2x minus 1/3 factorial and 2 sine of 2x?
Oh yeah, that's the step I was just stuck on, before I made it. And this is why this problem for calculus 2 asked in this way is a nasty question. I would say this is at least 2 times, to my taste, it's 2 times as hard as your problem 109 because it involves this very non-intuitive, c to factor out a half so you can see the power series for sine at the end. Like, is that obvious? I don't know. If you're more clever than I am, maybe it's obvious. I don't know. I mean, I know things. I know that the solution's a sine because I've studied differential equations. It's like I know what I'm looking for, which gives me a severe advantage over you guys. And even with that, in the heat of battle here this morning, I didn't see it right off. Right. I'm done. Do you guys have questions? Yeah.
How would you do this when you have to do the v equals dy dt?
V equals dy dt thing.
Yeah, like the last problem 120.
Here, let me get the projector out here. So I'm curious, did the top hat actually work yesterday? That's what I figured. We'll do it 2 times today to make up, 10 times today. But Zach is here.
Well, we'll just take his phone from him. I like him to send me the code with the PS, don't tell Zach.
I'm also doing this to a student in another class but there the other students are playing along with me and it's a small class. So like, even though the student is actually I think the boyfriend of one of the other students, you know, she gets the text, reads it, top hats, deletes it. So I mean it, and then I closed it down so you didn't get to do it. It was great. So much fun. So much fun. See, other professors use top hat, but I use it right. You know? Okay, problem 119 was your question? Oh, 120. Oh, yes. This is okay. So, it's actually very much related to what we're talking about right now. In class, remember we had a discussion at the end of it. One of you guys was like, "Is this on the test?" See, I remember that because nothing makes me sadder than when someone asks me, "Is it on the test?" after I've gotten through something that took me a while and I felt like it was interesting. It makes me sad. But I understand you guys have been taught. It has been drilled into your head by your previous instructors at various schools. You should always try to figure out what's on the test, and you should ask about it, right? And you should be verbal about it. You should, you know. And so I think that's been your training, so many of you, and so we shouldn't, you know, react negatively to it necessarily. It's just, you know, there's more to life than the test. I mean, there has to be a test, otherwise you don't go study, but we live in a fallen world. What can I tell you? All right, so this is the same problem solved a very different way. All right, so I showed you the power series solution. I would argue in some sense that that's easier than what we're about to look at. So we're looking at the problem y prime prime plus y equals to 0. And we want to, instead of using a power series solution, I want to show you how to solve it with reduction of order. So reduction of order says v equal to y prime. So what are we looking at? We're looking at dv dt plus y equals to 0. Right? This is problem 120. And I will almost solve it for you, but I'll just leave a little bit left for you to do at the end of it, okay? But, so that's the starting point, right? But what do I say in my instructions? I said using reduction of order, but then I also tell you to use my beloved VDV-dy trick, which we used in previous lecture to find velocity as a function of position, I think. So that here is dy dt dv dy plus y equals to 0. All right? In other words, v dv dy plus y equals to 0. Now, this is a first-order differential equation in v and y. We can try to solve this. How would you suggest we do it? So, yeah, so I heard do like this, v dv equals minus y dy. Is that right? Separate. Unlike the first example I showed you today, I think this one we can integrate, right? We don't need power series or anything kind of special. We can just integrate this, right? What do we get? 1/2 v squared equals to minus 1/2 y squared plus some constant, right? Well, I feel like it should be 1/2 a constant. So with that, look at what we got. We've got, you know, v squared equals to y squared plus a constant, right? There's a minus, right? Sorry, I'll get it eventually here. C minus y squared. And why not, you know, to make our life easier, what would make this pattern look nicer? Why don't we make that constant have a square on it? You know, why not? Fine, I won't do that. This is my physics training. We do things like that in there. Now, so this is what? We've got dy dt squared equals to c. I mean, you have to have the courage to go on in this calculation. So I'm afraid without my nudging, you might stop where we just got to and go, I don't know what to do with this, you know? But here's what to do with it. Solve for dy dt. What you got? What you got? You got dy dt is equal to, well, plus or minus the square root of c minus y squared. Right? And then, you know what we're going to do? We're going to separate and integrate one more time. See, because this is dy over the square root of c minus y squared. And I'll leave that pesky plus or minus up on the dt. I will integrate the right-hand side. I'll let you guys integrate the left-hand side. Get some other constant, like call it C2. How would you, what's this integral? Yep. It is an inverse sine, but that C is in our way, isn't it? How can we factor? See, now you see why I wanted to square the C, right? So why don't we let C equal to, say, beta squared for the sake of discussion. Then this integral is easier to think about. See, because then you maybe can see what the trig substitution you should make here is, right? Beta equals to, y equals to what? Y equals to beta sine theta, right? If we make that our trig substitution, shouldn't that should be nice, right? That'll eliminate the radical, won't it? So we got what? We got beta cosine theta d theta for my dy, and downstairs I got square root of beta squared times minus beta squared sine squared theta. How's that simplify? Yeah, the betas, they'd be canceling. And we got integral of cosine theta d theta. Oh, that's over the square root of cosine squared, yeah? So given the origin of the substitution, that has to be plus cosine theta, and they cancel, and we got integral of d theta. Which is, you know, theta plus a constant. Fine, I won't put the all right, I'll put the constant. Fine. I'll put the constant here, plus C2. I got to put the constant somewhere. Anyway, there, I'll put it there. And so what do I have? I have inverse sine of y over beta, right, plus C2. And that's all equal to what? It's equal to plus or minus t. All right, let me just, I'll write the conclusion down here. Plus, well, it's not the conclusion, it's just a step on the way. Right? Now to finish this thing, solve for y and rewrite the answer using the adding angles formula for sine and cosine. Well, for sine. Right? So you can solve for sine, right? Solve for y. What do we get? Y over beta equals to, I guess I could put the C2 on the other side. I'll make up my mind eventually, guys. C2 C2 sine of plus or minus t minus C2 in my current notation. But can you guys tell me how to, what's this amount to? This is sine of plus or minus t times the cosine of minus C2 plus the cosine of plus or minus t times the sine of minus C2, yeah? Can you simplify that? What does sine do to plus or minus? What happens to plus or minus when you feed it to the sine function? It comes right back out again, right? Because sine of plus, the plus just, I mean, properties of sine allows me to pull plus or minus out, in short. So I got sine of t, cosine of C2, minus the cosine of t times the sine of C2, right? This is all equal to y over beta. What's that make y equal to? Looks like plus or minus beta cosine of C2 sine t minus beta sine of C2 cosine t. And now it's just a matter of labeling. See, because if you look at the coefficients of the sine and the cosine function in the solution, they're what? They're like beta times the cosine of a constant, or they're beta times the sine of a constant, right? And if you think about that, that just means that they're an arbitrary constant. So just relabeling those arbitrary constants whatever you like, I don't know, what do you want? I'll call it C3. C3 sine t plus C4 cosine t. Maybe you can recognize that's the answer we derived the other class before I was asked if it was on the test. Yeah. I personally think that the power series solution to this problem is easier than what I just did. I think what I just did is very difficult for students at your level. And when I saw it in my junior level mechanics course for the first time, I was kind of flabbergasted by it. I was like, whoa, we can actually finish this calculation. Wow. I didn't know that was possible. So I probably wouldn't know this if I wasn't a physics major, is what I'm telling you. Guys have other questions? Maybe about simpler problems, please? Okay, go for it, Hannah. Can I do 104? I don't know. That remains to be seen. Hey, come on. You know, how long ago did I load? All right, Liberty, come on. Give me internet. Give you internet or give you death? Problem 104, we're supposed to consider 1 minus ax, use geometric series techniques to find the Maclaurin series for f of x. And let's see here. Let me make this bigger. Geometric series techniques to find the Maclaurin series f of x. Okay, so, you know, what I'm saying here is, I mean, from one perspective, we've already derived the power series for the natural log of 1 plus x using geometric series techniques, right? And so this problem, in part, I'm inviting you to go back and do that again, right? Go through those steps again. So we'll start with this. F of x is what? natural log of 1 minus ax, is it? And here a is a what? It's a positive constant, right? So can I expand that as a geometric series? Not directly, right? What do I have to do? Take the derivative. And what's that give me? That gives me df dx is minus a over 1 minus ax. Why the minus a? The chain rule, right. So I got that. Now this I can identify as the sum, n equals 0 to infinity, of minus a, parentheses, ax to the power n. Right? By the geometric series result, right? Don't make me explain the details because I will write I'm afraid if I do it, let me do it this way. Well, no, I better say that. If I explain to you why, I'll have to write a equals to minus a, which would be misleading. You know what I mean? Let me share with you something. AR to the n equals 0 to infinity, is equal to a over 1 minus r, right? So the trouble with this problem in some sense is it sets us up for a notational confusion if we're not careful. Because I've used little a for the first term in the geometric series. So if I just take a step back and say, you know what, I'm going to relabel the geometric series using big A, then I can say something cogently here. By geometric series with big A equal to minus a, and r equals to ax, right? Does that make sense? The point was I needed to change the notation for my default geometric series to make sure I could communicate it to you guys without saying something that was, not helpful. Now this comes with strings attached. What's the string attached? Needs absolute value of r less than 1, which in this case, means that the absolute value of ax is less than 1, right? Which, how can we simplify that? That's a times the absolute value of x less than 1. Why? Since what? What are we told about a in this problem? A is positive, right? Since a is positive. And so what do we got? We got absolute value of x is less than 1 over a. So that says to me that the open IOC for the answer is minus 1 over a to 1 over a. Now the endpoints are up for grabs. It may or may not be the case that those actually are points of convergence for the answer. If they are, I'm pretty sure that Abel's theorem says that the function is analytic at that endpoint, and it actually does match the function which we're modeling. Yeah.
I thought you integrated back.
Oh, we're not done yet. Yeah. Very good. Very, very good. And so he's like, why don't you integrate it back? That is a question I will find myself asking many of you on the test you'll take next Tuesday. Because you will get this far. You will do something. Having done something, you will have a sense of accomplishment. Having a sense of accomplishment, you will go on to the next problem, leaving some points left for me to gather up. But don't do that, because I already have enough points, I want you to keep them. But yes, that is a good question. We're not done yet. So like you said, integrate to get back. So f of x is integral of the sum n equals 0 to infinity of, well, minus 1 to the n, a to the n plus 1, x to the power n dx. Oh, I'm sorry, I have to integrate. Oh, yeah, I did integrate. Okay, great. So we pull the constant out front, okay? Great. Constant plus that. And so constant plus, well, sum, n equals 0 to infinity. And basically, we just pull the integral. We pull the integral. The term-by-term integration theorem says that we can take that integral and basically pull it inside the series is essentially it. You know, you can take that, move it over there. That's the term-by-term integration theorem, essentially. All right? So I'll just write it that way because I'm running out of board. And so what's the integral of x to the n? Well, you guys know x to the n plus 1 over n plus 1, right? Is a constant? It is. Search your, I said it was constant. So we divide by n plus 1. What I'm trying to tell you is don't integrate the a. You don't integrate the a. A is not something that's integrated. It's just a constant. It's riding along. X to the n integrates to x to the n plus 1. Right? Now that series starts at linear order. So when I plug in 0, what happens? Should I plug in 0? Can I plug in 0? I like to plug in 0. Why? Because it's easy to evaluate the series at 0. And I need to do that to figure out what that constant is. What is the constant? The constant should be f of 0. Looking at this, what is f of 0? Log of 1 minus 0. What's the log of 1? 0. Oh, the constant's 0. So we can prove that that's equal to 0. So therefore that is the Maclaurin series for this function. And that's what I intend with the instructions here, yeah.
How do you know the constant 0, though?
Oh, okay, so I guess I can erase this part now so I can show you over here. So f of 0 would be c plus the sum n equals 0 to infinity of 0. All right? So this is log of 1, which is 0, and this whole thing is just c. So we get c equals to 0. Now, yeah?
How did you get that first line for example of it?
Oh, here I'm integrating. Both integral of df dx is just f again, yeah? But that, I'm integrating this over here. Well, fair enough. Yeah, Hannah, you're right. I should really write one more step up here. I'm sorry, I combined 2 steps there, didn't I? So that's minus 1 to the n, a to the n plus 1, x to the n. So we do need to clean up the power series before we do the integration. Term-by-term integration theorem is for power series. It's not for things that kind of sort of look like power series but aren't actually power series. But no? Es no bueno? So there's a minus 1 to the... How did I get minus 1 to the n? Oh, you should not suspend disbelief. You should just not believe. Very good. So there's no n there. There is no n here. There is no n here. Thank you. Very good. Because it's not minus ax to the n. It's ax to the n. We would have got a minus 1 to the n in the answer if instead of being f of x equals the natural log of 1 minus ax, if we had been instead presented with natural log of 1 plus ax, we would have ended up with like a minus 1 to the n in the answer for a very similar problem. Listen, what if we set aside the instructions for this problem, right? Suppose we ask a slightly different question. Given that the natural log of 1 plus u equals to the sum. What is it equal to? N equals, how's it go? 0 to infinity of minus 1 to the n plus 1 over n plus 1 u to the n plus 1. Is that right? I believe we've derived this before, right? So this is, I mean, this is a result we could derive, right? With the geometric series technique. If I change the u to an x, you'd recognize it, right? If I change the u to an x, do you know it? Does that make it more recognizable? I don't know. I'm not sure what you've studied at this point. But that nonetheless is something we can derive with the geometric series technique. We differentiate once, apply the Maclaurin series to the derivative, and then integrate back. There, instead of having minus ax, you just have 1 plus x down here. So the r is equal to minus x. And so you pick up the minus 1 to the n, like that. Feels like it should be. Oh, I think it's not n plus 1, is it? What is it? It's just n here. All right, thinking through it. It's just n. Given this, find the Maclaurin series for that. How would you do it? And let me go back. Let me take the x and change it back to a u again so you can see the idea. So this is a different problem. Suppose you're given this. Find the Maclaurin series for the natural log of 1 minus ax. How would you do it? Right? You make a substitution. You use the known result. You simplify, right? What happens? What happens with these coefficients here? Notice the minus 1 to the n's cancel, just leaving us a minus. Minus a to the n plus 1 over n plus 1, x to the n plus 1. This should look familiar because it is our answer. Which way is easier? That depends on what you know, right? If you have the power series for the natural log of 1 plus something committed to memory, well, then my second solution is probably easier, right? But it comes at a cost, which is memorizing the formula, right? This is not one of the ones I expect you to memorize. So if I ask a question like this on the test, I would I probably expect you to do the geometric series technique. But if you did have it memorized, I wouldn't object to it. You know, I think it's reasonable that you know this series. So if I want to force you to do the geometric series technique, I will actually say the instructions something like, something like this, to let you know I don't want you to recite the log of 1 plus something from memory. But I do give you that freedom if the instructions are not so rigid. So the question is, how many tools can you sort of fit in your toolkit, and how much can you lift in your mind going to the test? I don't know. I had some friends in physics when I was an undergraduate that they would just memorize these really long formulas, and then like their solution would start with that. And it drove me nuts because I felt like it was my obligation to derive those formulas, and I would. But then the other guy would get like full credit from just writing down the formulas and going from there. I was like, hey. I mean, we did have like a sheet of notes or something that we could, maybe he didn't have memorized, maybe he had like on his sheet of notes or something, I don't know, but I digress. This is, I do think substitution, generically speaking, is less mentally intense when you can get away with it, right? Like if you can see a substitution method for a given problem, it's usually less laborious, right? I mean, you can contrast f of x equals to x sine of x cubed. Find the Maclaurin series, right? So if you were going to do Taylor's theorem directly, what would you be doing? You would be evaluating a zero, differentiating once, differentiating twice, differentiating 3 times, and so forth. Taylor's theorem would be a bear here because as you differentiate, there's product rules upon product rules upon product rules. And if you didn't have the insight to collect terms, every time you'd have more and more and more product rules, right? So like direct application of Taylor's theorem here would be a pain. On the other hand, a substitution technique to find the Maclaurin series for this would just look like what? And, you know, save yourself some writing. X cubed to the 2n plus 1 is what? So just and then there you go, Maclaurin series, no differentiation, right? All of the heavy lifting was done by a known result. The theorem I'm using, right, this is a theorem, is that the sine of u is the sum n equals 0 to infinity minus 1 to the n over 2n plus 1 factorial u to the 2n plus 1. And this, in a nutshell, is a lot of what mathematics is. This is finding theorems. What are theorems? Theorems are typically results which are true over a wide variety of cases. A theorem is typically some sort of important observation. That's what theorem means. Important observation. A theorem is essentially saying, hey, look at this. That's a theorem. And so when you find a theorem, usually it takes some work to prove it, right? But the thing is, if you remember the theorem, much like a black box, it saves you all of the work every time you use it. And that's what's happening here. We don't have to do the work because we already did the work to derive the Maclaurin series for sine. Just a point of philosophy, theorems are worth using if you can see them. For a long time as a math student, I didn't understand this. I used to just derive everything from scratch because I felt like using the theorem was cheating. Well, the truth is that not using the theorem was me just not being, well, mathematical. But anyway, you guys have other questions, perhaps? Yep. 118. Is this top hat ever going to load? I mean, come on, like seriously. I tell you, I just. Now I've forgotten what number you asked me about. What was it? 118. Okay. Oh, look. Let's party like it's 2098. Wait, 2998. 2998. Yeah. 2998. That's here. What did you ask me about? Problem 118.